In this video, we're going to talk a bit more about the linear no threshold model, because this model is absolutely crucial to the whole economics of nuclear power. Remember, the basic idea is that the dose of radiation you get is proportional to your chance of dying from cancer. It's not if you get above this dose you die, if you get below this dose you don't. Any dose can kill you, even the smallest doses. It's just the probability is very small. And this matters because these very small doses could potentially affect large numbers of people. For example, anybody who flies in an aircraft is exposed to a low dose of radiation. Anyone who has a medical X-ray is exposed to a low dose of radiation. If there's a nuclear accident, small amounts of radiation might spread over large areas. So a lot of the politics is about very small doses affecting very large numbers of people. And is it really true that a dose that's 1,000 times less than the lethal dose still gives you a 1 in 1,000 chance of dying? Or isn't it not? This makes a huge difference. And of course, as we've already seen, the data are hard to work out for these sort of situations. So let's think about the biology of why radiation behaves like this. Very large doses of radiation just kill cells by destroying so many molecules and enzymes and things within them they cannot function. That's clear. But we're now talking these very low doses. The basic idea is these ionizing particles are like bullets flying through and destroying random bits. And how much damage they do depends on which bit of a cell they hit and which cells they hit. Killing a cell by itself doesn't make much difference. The worst situation is if it hits a cell and causes the cell to change in such a way that it reproduces without limit, thus causing cancer. And so the normal idea is that the way this works is that a ionizing radiation particle comes through a cell and breaks the DNA. And there are many ways it could break the DNA without causing cancer, but maybe it breaks it in such a way that causes the explosive exponential growth and hence cancer. So you've got to imagine that it goes through and splits DNA. Now normally it can either split directly by actually hitting the DNA. More likely what it does is it hits a water molecule somewhere nearby and splits it up, producing an oxygen radical, and the oxygen radical breaks the DNA strand. Now the tricky thing about this is that actually you're getting oxygen radicals breaking DNA strands in every cell hundreds of times a day. In your body as you watch this, almost certainly that oxygen is causing DNA in your body to break. If every time oxygen caused DNA to break you got cancer, then no one would survive past 1 month old because there'd be cancer all the time in all the cells of our body. So it's very clear that we've evolved on a planet with background radiation and lots of oxygen, and the body must have evolved mechanisms to repair this damage. And people have looked into this biologically, and there certainly are these mechanisms, a combination, there's a whole string of different mechanisms, the DNA replacement mechanism, immune system, numerous things designed to stop these breaks from causing cancer. It has to be the case because otherwise we'd all have cancer from a very early age, because we're getting a number of breaks equivalent to about 100 millisieverts every day just from radiation, from oxygen. So we know we don't all have cancer, and we know that the body can repair the breaks caused by oxygen at low levels, and in fact the breaks caused by radiation are actually mostly caused by oxygen themselves. What's happening is the radiation hits somewhere else in the cell and produces the oxygen radical. So maybe it's the case that the body can repair damage if it only happens at a low rate, a rate comparable to what's happening naturally because of oxygen. Now the sort of breaks that are dangerous, if there's just a single break in DNA, the body can repair that within a day. The dangerous breaks are where you get a break and then before it's repaired there's another break, because that makes it much harder to repair. The body can still repair them, but if it's these double breaks that are the real dangerous things, and these happen naturally all the time, the body can repair them. So what's the evidence? How would you test this? Well, the standard linear no threshold model says that your chance of dying depends on the total radiation dose you get. It doesn't matter whether you get it all in one horrible day or a very small amount of radiation once a day for years and years, because the total number of breaks should be the same. But if the body can replace and repair breaks at some level, then the rate becomes very important. It's not so much the total radiation dose you get, it's how much you get all at once. If you get a dose all in one go, it can overwhelm your body. Whereas it's spread out, your body has can repair Monday's dose and repair Tuesday's dose before Wednesday's dose come along. So let's look at some data. Here we've got a number of people who've been exposed to various amounts of radiation. There are bomb survivors from Hiroshima and Nagasaki, people who were exposed in Chernobyl disaster, people who used to paint radium on watches to make them glow in the dark and got exposed to radiation from the radium, and a whole bunch of other random exposures that happen usually by accident. Of course, you can't deliberately expose people to radiation and expect to get away with it, I hope. Basically, what we've done is divided up at the top people who got all their radiation in one dose. For example, people who got doses during the atomic bomb explosions, and those who had doses of above 300 millisieverts, significant increase in leukemia, total doses of above 125 millisieverts, significant increase in solid cancer. So at rates of 100 millisieverts or above, it seems fairly clear if they happen all at one go, which of course it did. In Hiroshima and Nagasaki, most of the dose would have happened over quite a short period due to fallout and the actual explosion. And there's definitely an increase of cancer at above 100 millisieverts. Below that, less clear what's going on. Maybe it is, maybe it isn't. At very low doses, in fact, these people have less leukemia than average. And similar results are seen from, for example, Chernobyl first responders. These people got doses of 1 sievert to 16 sieverts, but all within less than 2 hours, and lots of them died. So no argument from me there. But now let's consider people who were exposed to radiation, actually very large amounts of cumulative radiation, but spread over a long period of time. Now the most extreme example is this guy, Albert Stevens. Now he was deliberately injected with plutonium back in the 1940s. This is a sense of very unethical experiments. This new radiation from the Manhattan program, and the US government wanted to know what it would do to people. And they decided to take some people who'd been diagnosed as terminally ill and inject them with plutonium to see what happened, given they were going to die anyway. That would not be considered an acceptable excuse today, but under the benefit of military security and national security and so on, it was allowed back then. Albert Stevens was thought to be mortally ill from something else and was injected with plutonium, but in fact his ill diagnosis turned out to be false. He was not actually going to die from other causes, and in fact he lived to the age of 79 and died of heart failure. And that's despite being injected with plutonium right into his body, which gave him a dose of about 8 millisieverts a day. 8 millisieverts a day for 20 years is 61 sieverts. That's 10 times a dose that if you get it all in one go, has a 50% chance of killing you. So that would be like a 500% chance of dying, but in fact he showed no particular ill effects. Another example here is an apartment in Taipei, where it turned out that by accident the steel rebar used in the reinforced concrete was quite radioactive from natural uranium. And the people in some of these apartments, that's 1,100 people, were exposed to up to 3 millisieverts a day for over 18 years. So that's a total of 4 sieverts, which would give them maybe a 40% chance of dying, naturally. But in fact, their chance of dying from cancer was less than that of their co-workers. And there are numerous other cases. If you get your dose in one severe go, it seems to be a good chance of killing you. If that same dose, or even a higher dose, is spread out over a large period of time, so you're only getting a few millisieverts a day, it doesn't actually seem to do very much damage. Now, the sample sizes are not very good and not very well controlled because you can't do this deliberately. I mean, no one deliberately set out to expose a bunch of people living in Taipei to radiation. It just happened. So you're relying on these natural accidents. So it's not compelling and the sample sizes aren't that huge, but it's at least interesting. So maybe what actually is, it's the rate at which you're hit by radiation and not the total amount that matters. Because the body can repair damage to DNA if it occurs slowly enough. And this suggests, currently, people are normally limited to a dose of 1 millisievert per year. That's the safe limits quoted, which is 3 times less than the typical background radiation people get. But maybe we could say instead of 1 millisievert a year, we could say we don't want to get more than 1 millisievert per day, which is actually what the safety limits were back in 1950. And that would mean, yes, you might get a very large radiation dose over your life, but as long as the dose per day is low, your body can naturally repair it. And even 1 millisievert per day is not that different to the rate at which things are happening naturally in your body from oxygen. And if you could make this change, I'm not saying necessarily 1 millisievert per day, but maybe 1 millisievert per week or something like that, that would make an absolutely immense difference. It would mean that the death tolls that people infer from low doses of radiation spread over large areas are actually not happening at all. It may even be good for you. Some people in Germany go and have radiation spas because the idea is that these low doses might actually be helpful to your body. And this could make nuclear power much cheaper if you don't have to worry about low-level leaks. It makes nuclear waste cleanup much easier and cheaper because radiation often won't cause damage above this level. And that will actually save a lot of lives, because if you can have more nuclear plants and dispose of the nuclear waste more easily, that means you can replace all the coal-fired power plants, and the coal-fired power plants definitely kill large numbers of people from their pollution. So maybe this could save a lot of lives.